Real QSP models have dozens of tubs, hundreds of pipes, and some drains are 1,000 times faster than others. Solving the full system step by step is expensive. The plumber needs shortcuts, ways to simplify without losing what matters. Some drains are so fast that the tub reaches steady state almost instantly. The small tub's water level adjusts to whatever the big tub feeds it, faster than the plumber can blink. So why track it? Set diff to 0 for the fast tub and solve algebraically. The fast tub becomes a formula, not a differential equation. This is the quasi-steady state approximation, the most common simplification in QSP. Drug receptor binding often equilibrates in seconds, while disease progression takes weeks. So removes the fast binding ode and replaces it with an algebraic expression. Fewer equations, faster simulations, same answer at the timescale that matters. If two tubs are connected by a wide pipe at the bottom, water equalizes almost instantly. The two tubs are always in equilibrium, their levels maintain a fixed ratio. Rapid equilibrium is like its cousin. Instead of setting one derivative to 0, you replace the forward and reverse binding rates with an equilibrium constant. The drug receptor complex is always at equilibrium with free drug and free receptor. This is valid when binding is much faster than everything else in the system, which it usually is. The bathroom tub fills in minutes. The basement tank takes days. When the plumber is tracking the basement, the bathroom has already settled. Its dynamics are invisible at the weekly timescale. Timescale separation splits the model into fast and slow subsystems. Solve the fast system to steady state, then plug those steady state values into the slow system. In QSP, receptor binding might equilibrate in seconds, cell signaling in minutes, tumor growth over months. You don't need millisecond resolution to track a tumor. Separate the timescales and focus on what matters. Which pipes matter? The plumber wiggles each valve slightly and watches every tub respond. This is the Jacobian, a matrix of partial derivatives showing how each variable responds to each parameter. If wiggling one valve makes a distant tub oscillate, you've found a sensitive connection. Sensitivity analysis ranks every parameter by its influence on the outcome. In QSP, this answers, does the drug's binding affinity matter more than the tumor growth rate? Does receptor density matter more than clearance? The answer tells you where to focus your experiments. And when one pipe drains 1,000 times faster than another, the system is stiff. The solver needs special care to handle both timescales without wasting computation. Sometimes the plumbing has rules that aren't rates. The total water in the house is conserved. That's an algebraic constraint, not a differential equation. When you mix ODEs with algebraic rules, you get a differential algebraic equation system. Mass conservation, steady state assumptions, and stoichiometric constraints all create DAEs in QSP models. And sometimes, one pipe is a mystery. You can see water flowing, but you don't know the equation governing it. Universal differential equations embed a machine learning model inside the ODE system. The neural network learns the unknown pipe's behavior from data, while the rest of the plumbing follows known physics. It's the frontier of QSP, combining mechanistic knowledge with data-driven discovery. 10 plumbing principles. Rate equations for how fast the level changes. Mass action for proportional flow. Michaelis-Menten for clogged drains. Numerical integration for the plumber's stopwatch. SA for instant drains. Rapid equilibrium for U-tubes. Timescale separation for fast bathrooms and slow basements. Sensitivity analysis for which pipes matter most. DAEs for conservation constraints. And universal differential equations for the pipes you don't yet understand. Every QSP model is a plumbing network. Now you know how to build it, solve it, simplify it, and test it.